All right, 11 o'clock. So uh, good morning, everyone. Welcome to OPAL-RT Learning Journey. First, let's introduce myself. My name is Wallace Aragal. I'm from OPAL-RT, and today I'm glad to have with me Brian Kidner, software engineer team lead at OPAL-RT, and our special guest from National Instruments, and I, Brandon Bryce. He's a principal solution marketing manager of EV testing. As you can see in our outline, we will have a presentation from Brandon about an overview about OPAL-RT and the NI partnership, how our joint solution addresses the challenges of performing EVs hard-in-the-loop testing. And after that, we will see, we'll watch Brian presenting the ITS demonstration. We'll see the whole system in action. And at the end of this webinar, we'll have question and answer periods. So please feel free to start sending your questions at any time. And at the end, we start answering them. Now, without further ado, I'll invite Brandon to start the session. Thank you, Brandon.
Awesome. Thank you for having me. It's a pleasure to be here with everyone. Kind of as Wallace alluded to, my name is Brandon Bryce. I am the marketing manager at our EV transportation business unit. A couple of things I wanted to talk about today. We're just kind of at its core, the partnership, and then kind of what we've been doing on our collaboration with the inverter test system that OPAL-RT and I have been working on. So at its core, really on the partnership side, NI and OPAL-RT have been working together for years now. This is, I say OPAL-RT is probably one of our top partners in this particular space when it comes to hardware-in-loop testing and real-time simulation. There's a few areas that we do collaborate on specifically. First and foremost is the Veristan Power Electronics add-on. This is really the, I'd say, the differentiator in our inverter test system offering and a lot of our power electronics offering. So the ability to simulate models on NI's FPGA hardware platforms is really what that power electronics add-on enables. Also systems integration for NI. So a lot of times when it comes to system delivery, integration, implementation, we lean on OPAL-RT a lot to actually do that. They have a strong expertise in that area. And then of course the SLSC module design and fabrication. So our switch load and signal conditioning platform which is really kind of what allows you to have that signal conditioning, that fault insertion capability in your systems. OPAL-RT actually designs a lot of the boards that go into our platform there. So looking specifically at the areas of testing and really inverter testing here, I think this slide probably isn't new to anyone who is kind of seen anything that we've done in the HIL space. But really, I just want to emphasize kind of the importance of being able to test earlier in the design lifecycle for your systems. So the more you can push earlier in the testing phase, the more test coverage you can try and get within that testing phase, essentially the lower cost your testing will be. And that's really kind of the idea here is, can we lower that cost of test? Can we iterate faster on the test? Can we find bugs earlier in your test system? And can you do it confidently? And confidence is really the big piece of it, because you need to be able to have that confidence, that level of realism earlier in the testing life cycle. And that's really where we look at kind of what type of simulation loop rates can you achieve? What's your model fidelity when you're trying to run power electronics models in your system? Those kind of things are the big care abouts really when it comes to testing earlier, but also testing more confidently. And that's ultimately going to lower the total cost of test for your test systems there. If we look at kind of the unique challenges specific to EV HIL, I think real-time simulation in HIL is not a new area for us. But as we've been transitioning more into the EV HIL test space, we're noticing some more and more unique challenges here that really the traditional HIL test systems weren't able to achieve. First and foremost, really is kind of that when you're trying to take old dynamometers or old test systems and convert them over to the EV HIL test space, you're really struggling to get that same level of test coverage on your systems, because it's not just an easy conversion from traditional HIL to EV HIL. And there's two really kind of big factors to that. The fast dynamic response of the power electronics inverters is really what makes that conventional HIL system unsuitable for EV. So you really need to have a faster simulation rate in order to catch that switching, or in order to model that switching in your power electronics circuits. And one of the rules of thumb here is kind of, we aim to say like power electronics simulation should be at least 100 times faster than your inverter switching frequency in order to just achieve 2% accuracy. So if we're saying 2% accuracy is kind of our goal already at this point, you need to be 100 times faster in your simulation than that switching frequency of your power electronic circuit. And so an example of that is if you have a 10 kilohertz switching frequency on your inverter, you need at least a 1 megahertz simulation capability for that system itself. And so that's really where we talk about how do we continue to iterate on, how do we continue to build on these systems in order to have that faster simulation capability, in order to basically get that level of model fidelity and that level of accuracy in your modeling that you're aiming for. And then we look at kind of what we try to do with the inverter test system specifically. As I mentioned, this isn't a new area for NI or OPAL-RT, but what is new is that we've decided to take a lot of what were just traditional components in our PXI platform, in our SLSC platform, and build that into a test system that is purpose-built specifically for inverter testing. And so the idea here is trying to minimize the complexity for your test engineers from a getting started standpoint. So having a system that's already built up basically mitigates the time it takes to actually integrate or build out your system. We're trying to get the signal paths out of the system quicker. We're trying to get the first communications established faster, and then getting models integrated as part of the tool chain. And when we talk about model integration, we also want to make sure that we can improve that model performance and maximize or optimize that workflow from your model in the loop to software in the loop to hardware in the loop, and then so on transition. So being able to re-leverage and reuse those models earlier from your beginning phases of design all the way through the system is one of the big areas of focus for us. And we do that by having a better integration and better performance with tools such as MapWorks, Simulink, and other integration or modeling tools there as well. So if we take a look kind of at the inverter test system itself, you can see kind of the measurement rack is really what we've talked about here. Brian will actually go more into kind of the measurement rack components, but really when we look at the test cell as a whole, our goal is to make sure that we're exercising that controller as extensively or as comprehensively as possible to try and make sure that we can find all the possible faults in our control loops and logic, making sure that all of the scenarios and safety situations that we implemented are executed efficiently and properly. And so we're doing that by basically modeling the world around the inverter controller, whether it be the power electronics, whether it be the electric machine, the battery, and then of course, being able to integrate into your existing infrastructure, whether it be your development machine, which has a lot of your test executives and scripting environments, as well as your modeling tools, or any type of server infrastructure you may have that does things like analytics or test results, or just kind of supervisory control. And so that's really what we're aiming to do, is kind of put this into the entirety of your test cell with the inverter test system, and make sure that we can maximize the existing investments you've already made while optimizing your efficiency from a design side. So with that, I will pass it back to us. Thank you again for having me, and pleasure to be here with everyone.
Thank you very much, Brenda, for the presentation. It was great to see this overview and how OPAL-RT and NI are working together. Thank you for that. Now let's move on to the demo that Brian has created. Let's see the system in action.
So welcome back to the OPAL-RT learning journey. My name is Brian Kinninger, and I'm a software engineering team lead here at OPAL. Today we're going to be talking about signal level HIL with the new inverter test system. So what is signal level HIL for inverter test? So everyone's vehicle has a computer inside of it. That computer is called your ECU, or electric control unit. The purpose of the ECU is to talk to, control, and coordinate between multiple subsystems in your vehicle. Some examples of those systems would be your battery, the traction inverter, the electric machine, as well as the powertrain. And what the ECU is going to do is it's going to be both putting out signals to control each one of these individual systems and collecting feedback from each one of them, and then trying to coordinate in an intelligent way to make it so that you can go down the road. And how are we going to test our ECU? Well, we know that testing in general with a true physical system can be quite expensive and a little bit dangerous. So what we're going to try to do is create models for each one of these individual subsystems, and then port those models onto a tester. But each one of these models has different requirements. Typically, those requirements are different types of signal mixes, but they also have different requirements for how fast the models need to execute. For example, an electrical model typically needs to run very quickly, something like 2 megahertz or faster in order to get good fidelity with your model. In comparison, something like your powertrain can be a little bit slower, maybe closer to 20 kilohertz. So we need to have a system that's able to take all of these different models and their different requirements and put them all together in a scalable but also cost-effective way. And that is what the inverter test system is for. So we're going to get into the specific features of the inverter test system, but first I wanted to talk about the high-level advantages of the inverter test system. The first being that this is a pre-validated set of hardware, and with that comes a quicker design cycle. That's because you know that the components that have been selected are specifically targeted towards the inverter test application space. The second thing is you're going to need some really high fidelity models. That's where the partnership between OPAL-RT and NI comes into play. OPAL-RT has 25 years of experience building real-time test systems, as well as proven models that have been used in dozens of customer applications. After that, you're going to have this improved configuration experience. This comes into place with NI VeriStand, as well as the power electronics add-on, which we're going to be talking about later in this presentation. And then finally, you're going to have faster development and faster procurement when it comes to your system. So it's great that you can vet one of these systems out to make sure that it meets your needs, but when you need to replicate, it's going to be faster and easier to obtain, as well as maintain your fleet of test systems. So before we get into the demo, I wanted to talk about the individual components of the ITS, starting with the hardware. There are 7 primary components of the ITS itself. So the ITS test rack is a 40U rack, which includes an emergency power off button, a power distribution unit, a power entry panel, an Ethernet switch, a fan control unit along with temperature monitoring, and it comes in 120 volt and 240 volt options for the power supply. So the first thing we're going to look at inside of the test rack is the PXI components. The PXI components include an 18-slot chassis, so you can obviously expand to more signal types as your needs change. It has an 8-core PXI 8881 controller, so we can run many models on the CPU in parallel. It has a PXI 7868R FPGA target, which is going to be executing our high-speed electrical models. That's how we're able to achieve that up to 2 megahertz of bandwidth models executing. And then it also includes a 6-port vehicle multi-protocol interface. And this is what's going to do our CAN and LIN communication. And connected to our PXI components is our SLXC chassis. SLSC is an NI platform that stands for Switch, Load, and Signal Conditioning. This is where we're going to be able to take our low power signals and signal condition them to a more application-specific channel mix. This includes a 12-slot SLSC chassis, once again allowing for a large amount of expansion of signal types. It has some low DIO options for maybe our vehicle body control signals, but then in turn it also has high-speed digital and fault insertion units for turning on and turning off our IGBT signals of our inverter. Then we have some analog outputs with fault insertion, and this is going to be used to give feedback to our controller for maybe our current transducers or voltage transducers, anything that electromechanically needs to be given to the ECU for it to understand the state of the vehicle. And then on top of that, we also have some general purpose AIO, as well as some resistive simulation. So if for some reason you have some sort of sensor that simulates as a resistive load, you can use that to meet those requirements. The ITS also comes with 2 unique power supplies. The first is the PS17 power supply, which is an instrument-grade power supply used to power your PXI and your SLSC chassis. And then separate from that is your RMX power supply. This is used to power the DUT externally so that if you want to test both high power or low power impacts on your ECU, you can use that. The final hardware component is the mass interconnect assembly. This is used to take all of the different signal mixes and bundle them up together into one high density connector that can then be used to connect to your device under test. Now let's talk about the ITS software stack. There are two primary software components to the ITS. The first is NI VeriStand, and the second is the OPAL-RT Power Electronics add-on. With these two, they work together to meet most of your application needs. But NI VeriStand is an expandable platform. So if ever you find yourself in a pickle without having the exact type of measurement you need, you can always create it yourself or talk to a partner like OPAL-RT. This presentation isn't going to be focusing on all of the different features, although you will see them in the demo. But I do want to call out some of the top highlights of NI VeriStand. Some of these features include RT stimulus generation, alarming, deterministic model execution, including advanced support for Simulink models, but there's a lot more features that go along with this, and we're going to see them in our demo. The OPAL-RT Power Electronics add-on is a plug-in into VeriStand, which is specifically targeted to signal-level automotive test applications. It provides a flexible and adaptive platform for your different electrical modeling needs, and it is released multiple times throughout the year, so we're always adding new features into the product. And it uses a licensing model which scales to your application's needs. The Power Electronics add-on is a VeriStand custom device which takes OPAL-RT IP and ports it onto the NI FPGA targets. This is what allows you to do that high-speed electrical modeling. Models include things like a circuit solver, but also electric machines, essentially everything that you need for your high-performance inverter test application. It includes multiple different types of machines, like a permanent magnet synchronous machine, induction machines, doubly fed induction generators, as well as an assortment of other different types of machines that are becoming much more popular in the automotive application space. Along with that, we're always adding in new ones as customers start telling us about new trends. Now that we've had a brief overview of the hardware and software, let's talk about the actual demo. So here I have my ECU, which is actually an OP-866 rapid control prototyping platform. It comes with 16 digital inputs, 16 digital outputs, and 16 analog inputs, and includes CAN communication. Basically, everything that you need to start prototyping your control algorithm. And the ITS will be executing a 2-level inverter model attached to a permanent magnet synchronous machine. What I've done is I've already created a VeriStand project with some of the typical user interfaces that you would see in an inverter HIL test system. This particular application is a field-oriented control of a PMSM electric machine. So what I've done is I've already closed the loop between my OP-866 rapid control prototyping platform and the ITS. And I've already opened up my project to VeriStand. Here you can see kind of the beginning starting point of what most applications would look like. You'll have a top level GUI, which gives you kind of the general feedback of what is happening in your hardware in the loop application. So my RCP controller is already controlling the simulated machine. And you can see that I can simply change the set point of the speed of the machine. And then my controller tries to follow the speed as closely as possible. And I can make it go in reverse. So now it's got negative RPM and then positive. Or conversely, if you don't want to do manual control of the speed of the machine, I've created a speed profile in VeriStand, and I can hit run. And what the speed profile is doing is it's giving speed set points to the OP-866, and then the controller then tries to follow those different RPM set points along the path, and then I can actually see what the impact is on the rest of the system. So here we just have some basic widgets of what the RPM is. We have our DC link voltage, DC link current, as well as what our active power that the machine is receiving. And if, for say, we have too much current, you'll start to see faults related to an overcurrent alarm in the system. And we'll see this a little bit later in a different test scenario. On top of setting the speed, I can also set the different torques. And then you can see that as I change the torque rapidly, the controller is trying to compensate by adding more current to the machine, thus causing it to speed up or slow down. So this gives you kind of a top-level visual representation of what is happening in our machine. We can then go into maybe lower-level views of what is occurring. So I have created a inverter circuit page. So here what I've done is I've taken my Simulink model that I loaded into the Power Electronics add-on. I've taken a screenshot of it and I've pasted it into Veristand. So it gives us a very pretty GUI so that we can understand what's happening. And then I've added the basic UI elements to understand what the current state of the circuit is. So from here I can see that my contactor, my battery contactor has been closed already, as well as I've put some kind of basic indicators of the status. So here you can see my iBattery, or the current coming through the battery. We can see that our DC link is being regulated at 830 volts. And then we can kind of see where the rest of the circuit pairs up to our machine, and where we can see our machine currents, which are currently sinusoidal. Conversely, I can give it a speed profile again, and you can start to see kind of how the currents are changing in the system dynamically. These graphs here can update at a speed of 290 kilohertz. I've chosen something considerably slower because I'm not concerned with that degree of granularity inside of the circuit. Also, this demonstration shows off the Power Electronics add-on scenarios feature. The scenarios feature enables us to be able to change parameters within the circuit in a microsecond step fashion. This is a really good way to test your inverter in a before and after scenario. So for example, you see that I have this RFAB resistor here. This resistor here is to show how the inverter reacts when I short two of the lines going to the machine together. So currently this resistance is set very high, like 1 mega ohm. But if I change my fault scenario to a phase AB short fault, what this is doing is it's using a Veristand channel to, under a microsecond, change the resistance between the two lines to be a micro ohm. So it goes from a mega ohm to a micro ohm. So this is how you show what it looks like when you short two legs of the machine together. And what's interesting is our controller is pretty good. It is able to continue to control the actual speed. So if I turn the speed profile on, you can actually see that the machine still is able to follow the speed profile, but my power is quite large, and you can see that I have overcurrent faults. So even though the machine is following my speed profile, it's in a state now where obviously the battery can't supply that level of voltage, and you would have to shut down your inverter. In this case, my inverter does not detect an overcurrent fault, and it continues to control the machine as best as it can. But in the real world, we would catch this fault and say that the inverter should turn off within like a millisecond of detecting this overcurrent situation. And so this is a really good use case to show how you can use scenarios directly in your test cases that you want to ensure that your inverter is covering. I'll go ahead and turn this fault off. We also have other faults. So a different fault maybe would be something like phase A to ground fault. So here is phase A, and now it's the scenario says reduce the resistance to 1 milliohm and then tie it to ground. And this is a very similar situation to the previous one, but you can see that once again, you kind of get these kind of these speed blips as the machine's trying really hard to control the speed. In this case, it's the PI controller is probably overtuned, and so it's overcompensating for one of the legs being essentially tied to ground, and we see all this different current. So the scenarios is a very powerful feature when it comes to being able to test things that a typical physical test system like an actual like the actual inverter would not be able to test. If you had done this kind of scenario with a real system, you would be popping fuses, or you would be supplying so much power that you would have to turn the tester off or limit the amount of current. And then on top of that, I created a GUI that gives us an overview of our actual code running on our OP-866 rapid control prototyping system. So this is my field-oriented control logic. So you kind of see what you would see in most field-oriented controls. You have a torque controller, which then cascades into a PI controller that controls our current in the D and Q axis. And then that then goes to our modulator or PWM generators. And on here, I actually have the PWM measurements that are coming out of the ITS. So if we once again hit our profile, you can see that as our currents change, our PWM duty cycles are changing along with it. This is a good way to troubleshoot your modulator on your inverter control system. And then real quick, let's go over to our debug panel. One of the things that I love about VeriStand is that while all of our models are executing, we can still change our UI to be able to visualize what is going on in the system. So in this case, the debug panel is just a kind of like a place where you just put all of the random things that you need to look at to make sure that you've set up your system properly and that there's no weird quirks going on. So if I unlock the UI and then go into the system definition where all of my channels are, I can actually drop down other circuits while the system is executing. So for example, let's put down maybe one of my measurements coming from my circuit. So let's say that the current in the C leg of the system is something that I'm interested in. And so now I can get live updates. And then the nice thing is that I can actually just delete out whatever I need and go back to locking the GUI so that I don't accidentally change something that I didn't want to. Yeah, so as you can see, there's a lot of features in VeriStand, and the Power Electronics add-on does a good job of complementing those, as well as adding features that are specifically targeted towards automotive inverter test applications. Thank you for attending the OPAL-RT learning journey about the new ITS system. If you need any additional information, you can contact us at OPAL-RT.com or reach out to your local sales.
That was great demonstration, Brian. Thank you again for showing us, all